Hello and welcome to another Introduction to Astronomy lecture. This is lecture number 10, Origin of the Solar System. In today's lecture, we will learn about the different types of rocks that are present in the solar system and what makes them geologically distinct. We will also learn about meteors, meteorites, and meteor showers, as well as how ancient meteorites and primitive rock studies can tell us about the past of the solar system. We also go into how meteorites are classified, which then brings us to solar nebula theory and a little bit about planetary formation. And then we talk about the evidence for solar nebula theory. So, when we want to study and sample the early solar system, the best way to do that is to look at rocks. So, there are three types of rocks found on Earth: sedimentary, igneous, and metamorphic. However, there is a fourth type of rock that does not exist on Earth anymore that is called primitive rock. Primitive rock is a very important way for astronomers to learn about the past of our solar system because it is original debris from the processes in which our solar system formed 4.5 billion years ago. And unlike lunar material, which can be collected, primitive rock is virtually inaccessible. But over many millennia, some primitive rock has made its way to Earth in the form of cosmic dust, which is always raining down on our planet, and meteorites, which are a little bit more sparsely raining down, but happen quite often on the grand scale of things. When comets travel through the solar system, they leave behind bits of material in the form of their dust trail and from their dust tail. And so, as Earth moves through the solar system in its orbit around the sun, it will pass through bits of dust in its orbit, and those fragments enter the Earth's atmosphere where they burn up and are referred to as meteors. So, meteors are composed of tiny bits of rock and dust which burn up in the atmosphere due to the friction of the particles of air. And on a clear night with no light pollution, you can see about 6 meteors per hour. If you're really lucky and you're really paying attention, but that's about on average. If you had like a full sky camera that could pick up and detect them perfectly. So these sporadic meteors aren't associated with any meteor showers, and they're just kind of randomly occurring events as the Earth moves through just dispersed random cosmic dust particles in the solar system. And so it's estimated that 100 tons of meteoric material burns up in our atmosphere every day and is spread over the planet. That's crazy. 100 tons. That's just really wild to think about in terms of it's always raining dust from space when you go outside. Now, more commonly known and often sometimes seen in the news or announced in the newspapers are upcoming meteor showers. So, dust trails from comets draw a path in the direction that the parent comet traveled. And so, when the Earth passes through particularly thick trails, we have very high amounts of meteor activity, which can last several hours. And we call these meteor showers. So the dust swarms that we see from meteor showers point in the direction of the parent origin. So this is called the radiant. So it's really clearly seen in this image, this video that we have below us, where the Perseus meteor shower is coming at us, and we see the arrows seem to all be coming from one point. That is known as the radiant point. And so cosmic dust is not uniformly dispersed by the comet, and so sometimes meteor showers vary in the amount of meteors they produce from year to year. Sometimes a meteor shower will be particularly good. Some years it won't be very good, but then the next year it'll pop off. So it's always worth checking out, just in case it's a really spectacular one. And the most prominent annular meteor shower is the Perseid meteor shower. And astronomers think that nearly 1 billion tons of dust material is in the Perseid swarm that was originally deposited by the Swift-Tuttle comet. Meteors from meteor showers, being little bits of dust from comets, have never survived trips through the atmosphere and made it down to the surface for us to study. However, we can send spacecraft out into space to go through the trails left behind by comets and collect the dust. So, using flight trajectories from these dust swarms, we find that the fragments are very light, not very dense, having a density of less than 1 gram per cubic centimeter. And so it's simply too unstable to survive at the atmospheric pressures of Earth and the force of Earth's gravity on it. However, uh, the NASA Stardust mission was able to collect some of this cosmic dust by trapping it in aerogel. So, aerogel is a very unique material. It's uh, very porous, very light, not very dense, but it's also very strong. And so it's used a lot in things like nuclear reactors. But in this case, they put it on the front of their spacecraft and just drove the spacecraft through the dust cloud. And the dust, some of it, was then collected in the aerogel, which they then brought down and were able to study. So in the previous slide, we were talking about comet dust meteors that haven't survived reentry. But there are obviously meteorites, bits of rock that have survived the entry into the Earth's atmosphere. And so these meteorites are from older times in our solar system and are from different types of bodies than comets. So these are fragments of the early solar system, and thousands of meteorites fall on the Earth every year, and they tell us a lot about the history and formation of our solar system. But the idea of studying meteorites to learn about the history of our solar system is relatively new, but people have known about meteorites for a long time. There's a very ancient and the only super ancient known meteorite that has survived for so long is the Kaaba, the holy black stone in Mecca. It wasn't until 1803, though, that it was really confirmed and widely accepted that these stones were indeed from space. When the French physicist Jean-Baptiste Biot observed a falling meteor which landed to Earth as a meteorite. So he actually was lucky enough to see this happen. And unlike meteors from cosmic comet dust, meteorites are composed very differently and can reach very large fragment sizes. And so during the descent, these can form groupings, and we see them fall as a shower of meteorites, which is different from a meteor shower. So when these larger rocks are entering our atmosphere and break apart into smaller ones, and then they all land, these are showers of meteorites, which are different from meteor showers. It's very confusing, the namings, I feel like, but we've got to pay attention to the orders and the suffixes that we're using. The ites refers to the fact that it landed on the surface. A meteor burns up in the atmosphere, or is it still in space, and a meteorite has landed. There are a couple ways of finding meteorites when they land here on Earth. One way is to watch them fall. And so when a meteorite is observed and its trajectory through the atmosphere calculated, a position can be given for its rough landing location, and then a search can be started. The media often reports that there are potential meteorite falls and sometimes falsely blame them for fires, but they are actually not very hot because they have frozen cores. So that fiery exterior from the friction in the atmosphere is immediately extinguished. And they even land with coatings of frost when they are found at the landing site. And it's very, very important. It's unlikely that you'll find a meteorite, but if you do find a fresh fall, you need to wrap it in tin foil or aluminum foil and put it in your freezer. I know it seems weird, but you want to keep the meteor interior as cold and as close to the original conditions that it had in space as possible, because the minerals inside are in a very like fragile, unique state, and as some of them warm, they will change composition. And so if we want to study the early solar system as accurately as possible, then we need to make sure that when we find meteorites, they are as fresh as possible. So if a meteorite lands in your yard, wrap it in aluminum foil, put it in your freezer, call NASA. That's just it likely won't happen, but if it does, I want one of my students to be the one that does it and does it correctly. So, just public service announcement with that. The other way that people find meteorites is meteorite finds. And so this is when someone finds an unusual looking rock and thinks maybe it's a meteorite. And so these are often rocks that have been laying on the surface for years, and so they have warmed and their compositions have changed greatly from what they were when they were in space or when they were a fresh fall. But scientists can still kind of calculate backwards and get a rough idea of what the original composition was, but it's best to keep a find as fresh as possible. And so often the public will send in a lot of samples for peculiar looking rocks for analysis, but quite often they are meteorongs instead of meteorites. Genuine meteorite findings happen very rarely, with only about 25 per year. But one place to find meteorites quite regularly is Antarctica. Antarctica is pretty barren, so there's not a lot of people to disturb it. There's really no wildlife to move things around, and there's not a whole lot of precipitation. So these space rocks are going to stick out very clearly, and because the cold conditions, when meteorites land in Antarctica, they still are able to preserve that interior composition in the same temperatures, and so they don't have as much degradation in their composition. More than 10,000 meteorites have been recovered from the Antarctic. So this is one of the best places to find meteorites and to then study this primitive material. It's very funny that one of the best places to study the early solar system is down in one of our forgotten continents, Antarctica. So now that we've got our meteorites, let's classify them. We've got our iron meteorites, which are nearly pure metallic nickel iron. You've got our stony meteorites, which are silicate rocky meteorites. And then you've got your stony irons, which are a mixture of stone and metallic iron. The irons and the stony irons are the most obvious to recognize as extraterrestrial rocks, because pure iron is very rare to occur naturally here on Earth, and is almost always an iron oxide unless it is man-made. However, stony meteorites are more common than the irons, and this makes it a lot more difficult to recognize which ones are actually stony meteorites. And so for those, you really need laboratory analysis to determine. One of the most significant distinctions is between primitive and differentiated meteorites. Differentiated meteorites have been subject to chemical changes, while primitive meteorites are the oldest material in our solar system. So that touches upon a little bit what I was saying about you want to keep those a fresh meteorite fall as cold as possible so it doesn't have those changes that make it a little chemically different. And by using radioactive carbon, or not necessarily carbon dating, but any radioactive dating technique on these primitive stones, they have been able to age them to 4.5 to 4.56 billion years, with an uncertainty of less than 0.01 billion years. So that's less than 10 million years uncertainty on that 4.5 billion year estimate. So that's pretty small margin of error. And this is based on the most accurate radioactive half-life measurements for the elements that are in these meteorites. When we really want to understand our early solar system, we have to look at these materials that have not been subject to any chemical changes, because we want to understand what it was like before things started changing. So asteroid spectra and the composition of primitive meteorites indicates that asteroids are often the parent bodies from which these meteorites broke off of. This suggests that asteroids are leftover material from the formation of the solar system. Studying carbonaceous meteorites has been pretty fruitful for astronomers because they have determined 16 amino acids, 11 of which are rare on Earth, but they can be found in carbonaceous C-type asteroids, as well as in these carbonaceous meteorites. So this is one link between the meteorites and the asteroids. And we can see that these amino acids have varying properties in that some are what we refer to as left-handed or right-handed based on the symmetry that they have. And so this is interesting because amino acids on Earth have only one symmetry. They are what we refer to as left-handed. So when we find these amino acids that have a right-handed symmetry, this confirms that they are from an extraterrestrial origin. It also suggests that complex evolution of amino acids is possible without the environment of Earth, and that complex chemistry must have occurred as the solar system was forming. Moreover, it's been hypothesized that these primitive meteorites might have actually fueled bringing organic materials to Earth after a period of hot formation on the planet may have not allowed initial amino acids to survive. So organic materials may have been introduced to Earth itself by meteorites. So we know that the solar system has to have been a vastly different place in the past than it is today. And we can tell this because many of the materials in our solar system have undergone and are currently undergoing changes. So despite the wide range of changes in the past 4.5 to 4.56 billion years, there are certain properties, certain basic properties of the planetary systems that must be explained by any hypothesis that is describing their origin. So these are constraints on our theory that, if left unanswered, suggest that your theory isn't right. So any theory that you have to explain the origin of the solar system must be able to explain the motion constraints, that is, that all the planets revolve around the sun in the same direction and approximately on the same orbital plane. And also, most of them rotate in the same direction that they revolve. And although there are some retrograde members of the solar system, all members of the solar system must have formed in a rotating disk of material at first. There are also chemical constraints, and this is that the giant planets are hydrogen and helium dominated with an abundance of carbon-rich compounds throughout the outer solar system, while the inner planets are rocky and metal-rich. And there's intermediate asteroids that are in kind of a transitional zone between the gas giants and the inner planets, and these have rocky and carbonic compositions. And then a theory on the origin of the solar system must also be able to explain the age constraints from radioactive carbon dating, which has confirmed that most of the rocks on the Earth's surface are nearly 3.8 billion years old. Lunar rocks are nearly 4.4 billion years old, and primitive samples from asteroids and meteorites suggest that they are as old as 4.56 billion years. And this suggests that these oldest ones, these primitive samples, are the original building blocks of our solar system, being the oldest samples that we have. This brings us to the solar nebula theory, which is one theory that is consistent with all of these constraints that we mentioned on the previous slide. And so the solar nebula theory theorizes that our solar system formed 4.56 billion years ago, which fits with our age constraint. It formed from a rotating cloud of gas and dust, which explains our motion constraint, which we call the solar nebula. And this solar nebula collapsed under its own gravity and coalesced as the cloud cooled, and this explains the chemical composition of our solar system. So we need to think about the physical mechanics of how a rotating nebula would collapse. As a rotating body shrinks, the body rotates with a greater velocity due to the conservation of angular momentum. You can think about this as an ice skater who is spinning, and when they have their arms out, they're not spinning as fast. They bring them in, they start spinning a lot faster, and that's the conservation of angular momentum there. And so when our solar nebula started to collapse, it started to rotate faster. The most abundant material then concentrated near the center, while the remaining material from the central point formed a disk with a little bit of a gradient to it. But the rotational velocity of the disk was not uniform, and material near the center collapsed. Near the center of the collapsed nebula moves more slowly and cooled quicker. The exception is that the material at the exact center, which is gravitationally concentrated and was very hot, and that was heated and dense enough to form our sun. So the terrestrial planets formed as the dust particles in the inner solar nebula started condensing and joining together through their own gravity into tiny bodies called planetesimals. So many of these planetesimals are still around today as asteroids and comets. And this explains why they have a light density. As planetesimals grew and got larger, some of them began to attract their neighbors in a process known as accretion. And so there are some intermediate steps that aren't very well understood. Eventually, these accretion centers began forming and growing larger in the inner solar system by the process of accreting more material until they grew to a subplanet size referred to as a protoplanet. These protoplanets kept growing from planetesimal impacts and accretion, and the impacts of planetesimals on the protoplanets gives off a lot of energy. That collision is going to impart a lot of energy and heat, and so that is going to heat your protoplanet and cause planetary differentiation. That is the separation of the heavier and lighter elements into the mantles and the crust in the terrestrial planets. During this process, many of the inner solar system planets lost those volatile compounds and left behind the heavier compounds, which could survive this intense heating phase. The formation of the giant planets in the outer solar system was quite different from the inner solar system, and this allowed the outer planets to reach much larger masses. The initial protoplanets grew much larger, and they were able to then attract the lighter elements like hydrogen and helium quite rapidly. This hydrogen and helium then collapsed gravitationally into the core of these proto-giant planets, and they were heated by the contractional energy of gravity. But unlike the formation of our sun, these planets didn't have quite enough gravitational heat to reach the concentrations and temperatures required for nuclear fusion to happen in their cores. Instead, after a period of being heated, red glowing phases, the planets eventually cooled down to their present state. This formation period ended when much of the raw material from the outer solar nebula was used up and the solar winds from the sun blew away any of the lighter gases which had not been swept up by these giant planets yet. So our young solar system was quite a chaotic and crazy place to be for those first few million years. And it's thought that this formation period happened relatively briefly in a few million years. Much of this raw material still exists today, but during those early years, we had tons of giant impact and giant collisions happening in our solar system, which helped shape the mechanics of the planetary motion that we see today. However, unlike processes of accretion, impact materials came from pretty much any direction in the young solar system because of the immense gravity of the giant planets, which was influencing all of this loose material. The giant planets influenced a lot of the distribution of how the material in our early solar system was distributed, and this resulted in the asteroid in the Kuiper belts, which we see today. There's also increasing evidence that this period of mixing materials and violent collisions was more impactful to the solar system than previously thought, potentially resulting in many gravitational changes to the planets. We can also use our very powerful telescopes like the Hubble telescope to look out into space and try to find other planetary systems that are in the process of forming their own through their own solar nebulas. So we can see a lot of circumstellar disks that are surrounding young stars with clear gaps in the material around them, which suggests that there's some planets that are gravitationally influencing that material surrounding these young stars. But it's very difficult to study exoplanetary systems because they are very far away and there's a lot of atmospheric distortion and a lot of effects that you have to account for. And so you gotta do a couple methods. Generally, they're found using Doppler shifts, which is looking at the spectroscopic radiation from the stars and looking at the gravitational influence of a nearby exoplanet affecting the star's radial velocity, causing it to wobble and giving it a little bit of a velocity shift, which causes a shift in the spectral data, which you can then estimate the mass of the planet from how much that shift is happening. There's also light curves, which is where you look at the amount of light being emitted from a star, and if an exoplanet passes in front of that star, the amount of light that you are seeing will drop a little bit. So if you have a sensitive enough instrument to look at a star, and you watch that star's light, and you can account for any atmospheric effects or any other such things, then when the star periodically dims, that has to be from a planet orbiting around it. And so with these improved techniques and technology, astronomers went from having no knowledge of exoplanetary systems to now having observed thousands, which suggests that there are nearly 50 billion planets in our galaxy alone. Planets are a very common byproduct of star formation, it seems. From our observations and our understanding of solar nebula theory, we have found some planets, exoplanet systems that do not resemble our own solar system. However, none of them have contradicted the basic idea of accretion and coalescing from circumstellar disks. We have to remember that using our own solar system as the universal model is probably a bit naive. Many stars form in more dense clusters, and so if you have the gravitational influence of other stars, perhaps you might not form planets in the same way that our solar system did with having just our sun nearby. But the existence of exoplanets in odd locations around their host stars has led astronomers to postulate that sometimes planets may experience what we call a planetary migration after their formation due to potential impacts or other gravitational influences. So this planetary migration is that it's possible that the orders of the planets in our solar system may have changed or moved around a bit. We can see in this graphic that it's been suggested that it's possible that if we had an extra ice giant planet in our solar system that experienced planetary migration, it might explain some of the properties of the Kuiper belt and the motions of planets in the outer solar system. But further support for scattering or planetary migration is found in the high eccentricity of many exoplanets. And this is a property not possible of planets that coalesce from circumstellar disks. In addition, it's not sure how these migrations might occur. We've just sort of seen what has been happening after the fact. And so gravitational influences might contribute. Many astronomers hypothesize that frictional losses occur when planets travel through debris, which might result in a spiraling out effect and cause abnormal orbits. However, it is unclear what might restrict the spiraling protoplanet from then impacting the central star. So it's really not sure. We're not quite sure the exact mechanics of planetary formation, but we've got a good general idea that seems to fit with everything we have observed so far. There are some irregularities, but in general, our theory of the solar nebula theory, seems to be well founded. This brings us to the end of our lecture on the early solar system and solar nebula theory.